In this lesson, we're going to take a look at the kinetic theory of gases, which relates to the temperature, kinetic energy, and speed of particles in a gas. And we do this by looking at what causes pressure, the impulse momentum theorem, and we make a couple assumptions. We assume that the gas particles only interact in a collision, so there's no potential energy going on here, and that all these collisions are elastic, which means we never gain or lose any kinetic energy. So remember, gas pressure is caused by a particle colliding with the wall of its container. Initially it comes in, it hits the wall, bounces off, and all these particles do this, and that leads to a force acting over an area, and remember, force over area is pressure. Now the impulse momentum theorem, if you recall from physics 1, says that the force that acts times the duration of that force is equal to the change in momentum, which means we can say force is equal to change in momentum over change in time. So we're going to use this to demonstrate or calculate the force a gas particle exerts. So we start with a gas particle moving to the left, and it hits the wall of its container, and then it bounces off and moves to the right. Well, momentum is mass times velocity, and this is moving in x, but it's negative. Afterwards, it's got momentum in x, but it's positive, and if we take final minus initial, minus and minus becomes plus, so we get that the change in momentum is actually 2mvx. We're looking for force, so we're going to divide that by time. Now, how much time does it take? Well, we're looking for the average force that's acting on the wall of the container. So how long does it take for these, over what duration of time are these forces acting? Well, essentially, how long does it take between collisions then? Because we don't want just the force at an instant in time, we want the force averaged over all time. So if we take a particle, it takes time for it to travel the length of the box and back. So this amount of time between collisions is the time we're interested in, and that time is given by the distance it travels, twice the length of the box, divided by the velocity at which it's moving. So that's what I subbed in here for t, or delta t, 2L over Vx. And then we do some simplification, and we see that really this means invert and multiply. So I went from 2mvx, my change in momentum, to 2mv squared x, because we have that other one, divided by L. Now, that's for one single particle bouncing off the wall, but there are hundreds of particles. In fact, there are n gas molecules in here. So we're going to go ahead and multiply this by n to get the total force acting over here. Now, you'll notice I went ahead and changed from mv squared x to mv squared x bar. That bar is indicating average. So we're taking the average force of each particle times the number of particles to get the total force acting on the wall. But remember, we're really kind of interested in pressure, and that doesn't just come in the x direction, that comes in all directions. So what I really want to do is I want not just Vx, but all velocities. Well, if I have something moving, then all velocities, when we're going to add up, we're going to do the vector sum of all the velocities in each direction. This is essentially the Pythagorean theorem in 3D. So the net velocity is Vx squared plus Vy squared plus Vc squared. But these gas particles are all moving in random directions, so it's a safe assumption to say they're all moving with essentially the same speed no matter what. So we're going to say Vx squared equals Vy squared equals Vz squared. Add those all up, so we get the velocity squared is equal to 3 times the velocity in x squared. Then, if we solve this for velocity x, we have velocity x squared equals 1/3 the velocity squared. And we're going to go ahead and sub that back into our previous equation, which said F equals n times mvx squared over L. Okay, so now we replaced Vx with just V, and so we have 1/3 or 3L. Now, remember, pressure is force over area, so we're going to go ahead and divide this force by area, which gets us 3AL, but area times length in a cube that has side length L is volume. So I'm taking this equation, and I've got pressure is equal to 1/3 nmv squared over V. Now, if I go ahead and rearrange this by multiplying both sides of this equation by V, then I get PV equals 1/3 N times mv squared. Now, there's a couple things that should pop up to us. This is the ideal gas law, because what we have is the ideal gas law, remember, says pressure times volume equals number of particles times R times T. okay? Capital T for temperature, which means we have pressure times volume over here. This must be equal to nRT as well. So that's kind of an interesting little thing. The other thing we might notice is this is mv squared. Well, kinetic energy is half mv squared. So we have two things that are going on here. We've got an energy introduction, and we've also got the ideal gas law. So let's continue this discussion. So remember, PV equals nRT, and that equals 1/3 nmv squared. Okay, so what's with the lowercase n and the uppercase n? Well, lowercase n is moles of particles, and n is number of particles. We use r when we're dealing with moles, but we use a different constant called Boltzmann's constant when we're dealing with actual number of particles. So we can actually, instead of using little n rt, we're going to use big N, Boltzmann's constant times t, and then we have this equality. Of course, the number of particles then on either side goes away, and we have Boltzmann's constant times temperature equals 1/3 mv squared. Okay, so that's kind of cool. Now, since kinetic energy is half mv squared, we're going to go ahead and we are going to try to get half mv squared over here. To do that, we're going to multiply by 3/2. That 3/2 cancels the 3 and it gets us a half. So that means half mv squared equals 3/2 Boltzmann's constant times temperature. Now remember, R is equal to 8.31, and that means you can do the math, but Boltzmann's constant is equal to 1.38 times 10 to the negative 23rd. And this would, of course, be joules per Kelvin. Okay, and it is very important that this temperature is measured in Kelvin, because the Kelvin scale is the absolute scale. It starts at absolute 0. We can't use Celsius or Fahrenheit for this. They don't start at 0. All right, so that means temperature is directly proportional to kinetic energy. Just like we claimed earlier, we said, hey, temperatures are related to the kinetic energy of the particles. Turns out totally is. Okay? Now, internal energy is the total energy of the particles in a system. And for an ideal gas, that essentially means kinetic energy. However, there might be some extra degrees of freedom, which we need to take a look at. So U is the symbol for internal energy. RMS is root mean square. Remember, we did everything in terms of average velocities. Okay, well, we're using root mean square. That's our average velocity. So the number of particles times half mv squared gets us the internal energy of all the particles, and we know that's 1/2 3 times Boltzmann's constant times the number of particles times temperature, which we can write also using R, 1/2 moles times 3 times R times T. Okay. Now, why is there this 3 right here? Well, that comes from the 3 motions that the gas particle had, right? It had motion in X, and it had motion in Y, and it had motion in Z. All of those could have energies because they can move in all those directions. Well, a molecule that contains 2 atoms can move in more ways than just X and Y, because it can rotate on its axes. Remember, we can have a vertical axis, we can have an axis that goes into and out of the screen, and we can have an axis that's horizontal. Well, if this thing is spinning on its horizontal axis around like this, its moment of inertia is very, very small. So that doesn't store very much energy. But if it's spinning around like this, or if it's spinning around like this, both of those rotations actually have quite a bit of energy. So we say it has 2 more degrees of freedom due to its rotation. We would have to account for that in a diatomic gas. Technically, there's also vibrational energy, but at room temperature, we don't really see anything contributing from vibrational. We see rotational and we see translational. So the equipartition theorem says that each degree of freedom contributes to the internal energy of the system, and that each contributes half nRT to the total energy. Which means if we actually had a diatomic gas, say like O2, that's got oxygen double bonded to oxygen, we would actually have to account for that. Which means if we consider something like neon, which is a monatomic gas, at a certain temperature, its kinetic energy is 3/2 nRT. if we had exactly the same amount of O2, same number of particles of O2, at exactly the same temperature, it actually has more internal energy. So on the monatomic gas, the internal energy is the kinetic energy, which is equal to this. But on the diatomic gas with the rotational motion, then our U is actually equal to 3/2 nRT because it's got all those translational motions, plus it's also going to have 2/2 nRT, oops, forgot my N over here, from the rotation it can have, which means it's got more internal energy at the same temperature, which is kind of neat.